Yes, please. Thank you.
So our next speaker is Preena Samuel, and the title of that her talk is Invariants of Mixed Tensor Superspaces.
Okay. Thank you, Professor Domokos, and thank you for to the organizers for having invited me to this short workshop. And I think I've been enjoying many of the talks in this workshop. It's a nice uh, set of speakers which we've got. Well, so I'll start off with something that we are all familiar with, and which has an example which has made its appearance multiple times in various talks in the last 2 days, and that is the case of GLN acting on M and K. So let me make a disclaimer in the beginning itself that the underlying field I'll be working with is almost everywhere C. It's going to be C, and we have the GLN action on matrices. Now this is several copies of matrices, and the action is via simultaneous conjugation. And the fundamental questions was is so when you look at the invariant ring, the generators and relations to understand them is one of the fundamental questions. And of course, this is a very well-known problem, and it's well addressed already in fairly large generality of K. But I would like to rephrase the same question in a with a mild modification, which is essentially to enable me to generalize it to the setting that I'm interested in, which is instead of looking at Mn of K, I would think of it as endomorphisms of a finite dimensional vector space of dimension n, and the GLV acting on end V. And what we are asking is, can one find generators and relations for this ring, the invariant ring here? And the approach that is the standard approach, at least in characteristic zero, is to use Schur-Weil duality, and which is basically you look at GLV acting on an R4 tensor space, which gives you a map like this, and one wants to understand what are the endomorphisms which commute with the GLV endomorphisms here. So the GLV endomorphisms is what we're looking for, and the answer, of course, we know is given by Schur-Weil duality. But how do you go from here to the invariant ring that we are interested in? It's via some set of canonical and isomorphisms or well-known isomorphisms, which are, for example, here you have end V identified with P tensor V star, and this is a canonical isomorphism which we have, where we the left the so on the left hand side you have these you can talk about trace and multiplication, which translates on the right hand side in a nice way. So also we can, so this is still in NV. Now, how do you reach the invariant ring? It's via these sequence of isomorphisms, which are all very well known. Again, this comes from some non-degenerate pairing that we have from between NV tensor R and this object inside the bracket. And then rearranging, you get this isomorphism here, and then finally using the canonical isomorphism between V tensor V star and NV, you get to this space. And now we have reached this object on the right hand side, which is nothing but multilinear functions on end V cross R. And from there, one knows how to go to the polynomial functions, which is the process of, at least in characteristic zero, this is by the process of polarization and restitution. Now, so now all these isomorphisms involved are GLV isomorphisms. So one can start with GLV invariant endomorphisms here and land up with GLV invariant multilinear functions, and then using the polarization operation, you land inside the invariant ring that we are looking at. And here one knows that this is going to be spanned by the permutations on R symbols, that is by the symmetric group on R symbols acts on B tensor R via place permutations. So that's the standard approach. So that's the underlying idea in this very old paper of Prechici from 1976, which basically gives you a description of the invariant ring that we're interested in. Again, I've written it in a very messy form, basically keeping what a generalization I have in mind. Well, so in this form, probably the answer doesn't look very cute, but definitely if you replace it by matrices, so identify V tensor V star with the matrices R copies of M and R, then what you have is just that this result translates to saying that the invariant ring is generated by traces of monomials. Well, that's where we start off with, but quickly we'll look at some generalizations of this statement. So we are looking at this invariant ring. One obvious generalization is to replace GLV by, say, some classical groups, and much of this is already addressed in characteristics over C, for example, is done already in the paper of Purchasey, which I've already referred to. Well, that's not the direction I want to go, but let's look at the other possible generalization, which is what is invariance of quiver representations. So now you have a quiver and you have a representation of it, which means you have a collection of vector spaces, finite dimensional vector spaces, and maps between. So if you have two vertices and an edge, so this is your collection of vertices, and this is a collection of edges, and you have maps. So basically, what you have this representation, and what one knows is that you can. I mean, so one looks at the GLV alpha for each of these V alphas. You take this copy of GLV alpha. It naturally acts on this representation space, where by the representation space one means it's a direct sum of these Hom spaces where all these lie, where these homomorphisms live. So that's your representation space. So if you replace your end V cross R by this direct sum of Hom spaces and GLV by this group, then one can again ask what are the invariants. And of course, this is studied for because quiver representations have to do with representations of finite dimensional algebras. There's a whole lot of work done in this direction. And one observes that the case which we started off with is just a special case of this quiver representations, because you could take the R loop quiver with one vertex and get precisely what we had looked at earlier. Well, so that's quiver representations, and that's still not. And yeah, so the answer in the quiver representations, I'm just mentioning some very old result, but of course, there's lots of results in this direction, which I'm not even alluding to. But let's move on to the other generalization, which is invariance of mixed tensors. So first of all, what do I mean by mixed tensors? It is a direct sum of it's a direct sum of these kind of tensor spaces. These are some copies of V and some copies of V star tensored together, and then you take many of these kind of pieces together. This is what I would mean as my general definition for what a mixed tensor space is. And I retain the same group GLV acting naturally on this mixed tensor space, and then replace end V cross R by this mixed tensor space and ask what are the invariants. So that's the generalization I'm going to look at. Well, the first thing what I would like to do is motivate why we look at mixed tensors. Why is this an interesting space to work with? Which comes from understanding. So mixed tensors come up naturally when you try to look at invariance of isomorphism classes of various algebraic structures. Well, just to give a hang of how this works, I'm going to illustrate it in the example of Hopf algebra structures. So let's take finite dimensional Hopf algebra of, say, dimension. Let's fix a dimension n. Then the possible Hopf algebra structures. So when I just to recall, when you say something is a Hopf algebra, it's a vector space along with a set of maps satisfying some commuting relations. So this is what is called the multiplication map, the co-multiplication. You have a unit and a co-unit map, and then there's an antipode map. And there are some commuting relations which have to be satisfied. So that's what I mean by a Hopf algebra. So so now how does mixed tensors come into this picture? So for every Hopf structure, so let's say this is a Hopf structure on Cn. So there are these maps which satisfy some commuting diagrams. We got to associate a tuple, a large tuple, which lives in a large affine space. But how do you associate them? You just look at the structure constants of these maps. So what by a structure constant, I mean you fix a basis of Cn. Let's just take the standard basis and then look at the action of look at this map and express it in terms of this basis and whatever are the scalars appearing there. That's what we're going to call the structure constants of this map. So for each of these maps, you have these associated structure constants. That gives you a very large collection of coordinates. So for every Hopf structure on Cn, you associate the set of coordinates. And what you notice is that if these commuting diagrams are to be satisfied by these maps, it will translate in terms of these coordinates to some relations like this, some identities like this to be satisfied among the coordinates of this associated tuple. Notice that these are all going to be closed conditions, and therefore the variety that one can look at the zeros of these relations, and that will be a variety. It will be a closed subvariety of this large affine space, and this is what we're going to call as the variety of Hopf algebras of dimension n. Why is it called so? Because you notice that for every Hopf structure on Cn, there is an associated point inside HV, basically satisfying these relations. And if you give me a point here, I can give a Hopf structure on each the other way. Well, now how does mixed tensor still come in is not clear, but point is when you start with two Hopf structures on Cn, let's say H1 and H2 are two Hopf structures given on Cn, then there are these associated tuples on the other side. Now, if I know that there's an isomorphism between these Hopf structures, that means there's an isomorphism of Cn, which preserves these maps. That translates to saying that these two tuples that you associate here to H1 and H2 are in the same GLV orbit. Now, how does GLV act on this side? It acts naturally, where by naturally I mean that I realize this affine space as actually the under a choice of basis for V. I can identify this large direct sum of Hopf spaces with this affine space. So there is a natural GLV action on this Hopf space, direct sum of Hopf spaces, and that translates to an action here on this affine space. Fine. So when we look at two Hopf structures which are isomorphic, the corresponding GLV, the corresponding tuples associated to these Hopf structures are going to lie in the same GLV orbit, and converse is also true. So isomorphism classes seem to have to do with the orbits of GLV orbits inside HV in particular. So obviously there kicks in the invariant ring kicks in there. So we're looking at KHV, GLV, the invariant ring of K. This is the coordinate ring of HV, and the GLV invariance there. And notice that this large thing can be just thought of as this strange mixed tensor space in the generality that I have defined it. So this turns out to be a mixed tensor space. So if you know invariance of this GLV action on this mixed tensor space, you can push it down to get generators. Generators here will push down to give you generators on this side, and that's one way of constructing separating sets. So in fact, this is the idea that was used in a recent result of mine, where I've actually come up with some finite collection of separating set of invariants for this variety HV. And for small dimensions, the problem is that these separating sets only invariants, what they do is only tell you if there is a one invariant where these two Hopf algebras take different values, they're not going to be isomorphic, but it doesn't tell you the converse. So if you know that both two Hopf algebra structures correspond, I mean, if you evaluate on the corresponding tuples, you evaluate these two invariants, if they turn out to be equal for all the elements of the separating set, it doesn't in general tell you that H1 is isomorphic to H2, but for certain small dimensions, it does. So that's the motivation for, that's an illustration of why we look at mixed tensors in the first place. So now we are still going back to our original thing, that we are trying to replace this by the mixed tensor space and looking at the GLV invariants. Now this is actually addressed in a very old result, 2005 result of Dutt Kodialam and Sundar, where they give a general way to approach this, so how to get a generating set for the invariants of the mixed tensor space, and they use what are called picture invariants, which is I'm not going to go to the details of this, maybe to save a little bit of time for things to be done later. So here it's called picture invariant because there's a specific picture that one can associate to, and to explain this, maybe it's only it probably is a little bit of a digression. So let's just say that the picture invariant is some polynomial of this kind, and uh, so these picture invariants, of course, are one wants to see that whether this whole thing can be lifted into a supersetting. So we now replace the vector space of n-dimensional vector space now by a super vector space, which is nothing but a Z2 graded vector space. So it has a even and an odd part, and all these are finite dimensional. And so we want to look at the same problem now in the supersetting, which means that we have to make sense of all the ingredients in this. So we start off with the super vector space. So we're looking now at the category of finite dimensional super vector spaces. Now the problem is how I mean the difference comes from, so this gives you really a parallel world that you're working with. So from the classical theory, you work now in a parallel setting where I would say the underlying culprit is this braiding, which is a way of identifying V tensor W with W tensor V. So we are looking at the super vector spaces of finite dimensional, which is along with this braiding that we fix. So what we have is so if you want to look at this object, of course we are now trying to do a parallel theory. It doesn't fit into what we classically know, but some parallel world is to be constructed, and much of the work is of course done. There was not it's all borrowed information, but yeah. So first of all, end V, we can make sense of this. It's still the space of all linear endomorphisms of V, but now this is turns out to be a superspace. It has an even and an odd component, where the even part is those endomorphisms which preserve what is called the parity. So this number 0 and 1 is what is called the parity of a vector. So if a vector comes from v0, we say its parity is 0, and that from v1 it's parity 1. So end v0 is those endomorphisms which preserve parity, and end v1 is those which reverses parity. So of course, this can also be lifted to any Helm space. And if you take two super vector spaces and look at the Helm space VW, it again has this decomposition. It is again a super space. So in that sense, V star is also a super space where the even and the odd parts are the duals of the corresponding even and odd parts of V. Okay, so that this is something that we understand. And now, the first thing before I get to the other ingredients here, one notices that if we want to, so the idea is to pull through the classical line of proof into the supersetting. So, which means we need to have some way of going from endomorphisms of V tensor to the dual. And of course, the whole thing can be worked, but it's just that now the isomorphisms have to be reworked in this parallel world, where the braiding is going to clearly wreak some havoc. And that's not a very serious business, but it can be done. These isomorphisms can be lifted to this braided category. And so that's about the first ingredient in the proof, if at all we manage to make sense of this. So now moving on to what we really mean by GLV. Here, first of all, when we have V, you have this associated endomorphism space, and the one gives describes what are called Lie superalgebras, and this turns out to be a Lie superalgebra, which is what is called GL of V. And there's something, so this is Lie super bracket defined on it, which satisfies some modified Jacobi identity. Now, this is a very well studied theory, the theory of Lie superalgebras, and there's in fact a nice classification result for finite dimensional Lie superalgebras due to CAC. And so that's still, we are still in the Lie algebra, and we want to make sense of GLV. And there are various ways to define this supergroup GLV, which have been there are various approaches which have been taken, but the most popular is the one which uses the notion of what are called group functors and superschemes, essentially an extension of algebraic geometry to what is now called as algebraic supergeometry. So what is this object? We first think of it as a functor so it's a group functor from the category of superalgebras. When I say superalgebra, it's an algebra with which is not necessarily commutative, but it's super commutative. So it's graded, Z2 graded, and has super commutativity relations. So this category to groups, we give a map, which is we give a functor, which is taking a superalgebra to the all invertible automorphisms of V tensor A. So VA is just extended scalars to A. So it's automorphisms of VA, but those which preserve parity. Okay, so it's not all the automorphisms, but only the even part of it. So that's the functor that is associated. And it turns out that this is representable, and this is the scheme that's the group supergroup that we want to associate to this. So this is what we mean by GLV. It's the supergroup here. And how does GLV act on V? Again, because we're working with a functor, we'll make it act on this functor of points associated to V. V is a vector space. You associate this functor of points, which is on an A, it evaluates to not the entire V tensor A, but the even part of it, the degree 0 part of it. And this obviously acts on this so the A valued points of this group acts on V of A. So that's how the group this group GLV acts on this functor. And this functor is going to be representable if V is finite dimensional, and the coordinate ring, if one wants to call it, is going to be sim V star. Sim V star is the quotient of the tensor algebra of V star. Well, now so we made sense of this, we made sense of this object, and so the whole thing does make sense. But the point is here I'm going to make a shift to actually looking at this, since we're going to be interested in explicit generators, we're going to look at t valued points for various super algebras. But the standard tech approach here, and or the standard technique, well, I shouldn't call it a technique, but the strategy here is usually to take t-valued points for a very special t, which is the infinite Grassmann algebra. So we are not going to look at this question, but look at actually the lambda valued points of this group acting on so now w is raised, scalars are extended to lambda, and then we look at sim w lambda star. So this is the new thing that we're going to look at, and so this is an actually explicit concrete calculation one can do. And here lambda is what is called the infinite Grassmann algebra, which is nothing but the direct limit of these exterior algebras. So this is a directed system for as n varies, you get a directed system, and this is the direct limit of that. So this is the algebra. The good thing about this is that it, unlike C is purely an even. It doesn't have a odd part. It doesn't have a odd degree part. It's, so thinking of it as a super algebra, it only is a purely even super algebra, while lambda has a pretty large even and odd part. And so now the whole thing is now shifted into actually concrete thing of concrete calculations of looking at lambda valued points of GLV acting on sim W lambda star. Now, so now we can go back and see if we can lift the classical, the idea in the classical case, and for which we of course need the main ingredient, which is Schur-Weil duality in this setting, and that turns out to be true in by a result of Sergeev. In fact, this is probably also due to Beryl and Regev from a much older paper in 1988, where they show that if you look at so this is phrased in terms of the Lie algebra first. So the Lie algebra GLV lambda, which is GLV tensor lambda, and the even component of that is taken. So that's this even component somehow comes into this Schur-Weil duality, because this turns out to be the Lie algebra of the supergroup that we are looking at. So the Lie algebra, the supergroup, will be just the even part of the GLV that we started with. So, so we have a centralized so a Schur-Weil statement for the Lie algebra, which can be easily lifted to a supergroup setting. So a supergroup version of this can be what to say, phrased, and it is true that this if you replace this by the supergroup GLV lambda, then this the centralizer of or the things that centralize GLV lambda is coming from just lambda SR. Okay, lambda SR is the symmetric group with scalars in lambda, the group algebra over lambda. And how does SR act? Again, SR doesn't act in the classical, the usual way, because now we're working on a superspace. There's some sign involved in this action, and with respect to that action, this turns out to be, these two things turn out to be centralizers of each other. Well, yeah, so that's basically, we have all the ingredients now. So one can get ambitious and try to extend this ideas from the classical case to the super setting, and it does work through. So there's some way of doing this restitution and polarization process as well in the super setting, and this is what was exploited by Beryl in 1988 in his in which he has actually given a very it's an analogous statement to that of Prochesis in the super setting. And it in fact has a very similar look, but now the trace is now what is usually called a super trace, which is not precisely just phi of v, but there's some sign involved here. So the invariant ring turns out to be generated by super traces of monomials. Okay, so that's in the that's the case where we worked with NV cross R, and as we did in the classical case, we're looking at these generalizations. The QR representations has generalized as a generalization to the super setting as QR super representations, and this is some recent work of Zubkov and Bowlby, where they look at the invariant ring there, and they seem to they have some results on the invariants and semi-invariants, in fact. While here, what I'm going to look at is the mixed tensor superspaces and the invariance of sim w star GLV lambda. Okay, so we are trying to get generators for this sim w star GLV lambda. And the answer is again very similar to what it was in the classical case. which is there it was generated by picture invariants, and for want of a better term, we're going to call these as graded picture invariants to differentiate them from the picture invariants in that they're not precisely the same polynomials, but of course there's some sign coming from all these various the braiding of course plays a role there. So this is some signed sum of these kind of terms which appeared in also the picture invariants. So that's the and the idea of proof is essentially to go through these various isomorphisms to start with the sure while and land inside the invariant ring, which was what I alluded to in the beginning of this talk. The approach is to go from sure while duality to the polynomial invariance, and that works through in the supersetting as well. And so in one notices that this is a special case of, I mean, this is a generalization of the Beryl's result, because if you take BI to be 1, what you precisely get is what Beryl has explored in his paper, which I'm referring to a much newer paper because I think the statement is more explicit in this 2013 paper of his, where he also does the case of QR. So instead of GLV lambda, he looks at the QR supergroup, which is the supergroup associated to the Lie superalgebra, the pure Lie superalgebra. So that appeared in the, if you see in the list of simple Lie superalgebras that was given by CAC, the pure superalgebra, pure Lie superalgebra makes its appearance there, and the group associated to that is what is called the Cure group. So we also have done the same lines. We also have extension of this mixed tensor space to the QR setting. And the in the case where Ti is equal to Bi is equal to 1, it these results, this picture invariants turn out to be precisely what Beryl had got in this earlier paper. Well, so this is joint work with Santosh Patnaik, and it's still just posted on the archives, so it's not yet published work. Well, I think that's about it. Thank you for your attention.
Thank you very much. Are there any questions?
Hello, Matesh. Can I ask something?
Yes, sure. Go ahead.
Okay. I don't see myself. I don't know what's going on with my camera. Uh, nice to see you, Preena.
Nice to hear from you. Yeah.
So I have a question. Why? I mean, about your choice. Why queer supergroup?
Why Cure supergroup? It's basically coming from the, so the idea, sorry?
Okay, go ahead.
Yeah. So it comes from sure while. I mean, because the extensions of sure while are not known for many of these. I mean, if you want to, yeah. So the super analog of sure while for a supergroup is known for the Cure, and that was naturally one could try and extend whatever ideas we have used for the general linear supergroup to also the Cure group. So that's a very mundane reason, I guess. I don't think there's more invariant theoretic inspiration.
I see. I understand it. But probably you can reduce the action of general linear supergroup or queer supergroup to the induced action of its Lie superalgebra, right?
Sorry,
Because
I didn't.
you are working in characteristic zero, right?
Right.
So therefore, the action of supergroup can be just replaced by the induced action of Lie superalgebra.
Right. Yeah, absolutely. Yes.
So you are working with you're working with the action of Lie superalgebra.
Yeah.
Yes.
True. Yes. Yes.
In which case, I think that you don't need really these coefficients from infinite Grassmann supergroup. You can work exactly.
Well, I am not sure. So if you so the attribution to all these versions of sure while duality is due to Sergey. So there's this paper of Sergey from 2001 where he gives all these so essentially analog of much of Procesi's work is done there, but everywhere he does work on lambda, that is the infinite Grassmann algebra, though I am not very sure I have enough insight to why they extend scalars to lambda and not do it over or general superalgebra? I mean, why is it why specifically? So the only reason, as far as I know, is that it's motivated from the physicists' interest in the infinite Grassmann algebra. But yeah, Sergeyev's results are also over the infinite Grassmann algebra. So the Lie algebra statements of Schur-Weil is still with lambda valued points.
Okay, I think probably I have to think about it. Right now.
Yeah.
I'm not sure, because for me it's more natural to use the group superscheme language, which is, I mean, the language of k point functions. You know this language, right?
Yeah, it's just a language. Yeah.
Okay. So,
Yeah.
never mind.
But yeah, even if we try to do it, the thing is, yeah, we will still have, yeah, as you said, we can still try for other Lie superalgebras. But then what we will have to do is look at lambda extension. So lift this question to the infinite Grassmann, extend scalars to infinite Grassmann, and then try to do it, which we haven't tried. I mean, so far we haven't tried attempting anything of that kind yet.
Okay. So another question. Is it possible to extend your technique to another basic supergroups, like a periplectic supergroup, for example?
Periplectic? Yeah, so I think one reason this mixed tensor spaces don't make much sense in many of these supergroup cases is they turn out to be, so V star V is self dual in finite dimensional case. So we're not really saying anything very new if we look at mixed tensors. Then that's probably periplectic also is not a very interesting case to try out.
Yeah, both orthosymplectic and periplectic. So they're self-dual. The natural representation is self-dual. So they're nothing but the first fundamental theorem. They're done by Lehrer and Zhang. So there is nothing new.
Okay, I see. Okay, thank you.
It's just FFT. Yeah.
Yeah.
So good. Thank you, sir.
Thank you.
You mentioned as a motivation classification of Hopf algebra structures. Is there literature of that kind, the study of classification of
Yes.
structures?
For example, semi-simple Lie algebras. There is a analogous thing that is done there. So invariance for isomorphism classes of semi-simple Lie algebras is what is done, because the crucial thing is if you want to distinguish isomorphism classes, you want them to be closed. So you look at a subvariety there, which even if it's open, there's some way of getting around that, which is to look at semi-simple Lie algebras, finite dimensional semi-simple complex Lie algebras, and try to give invariance for if you fix a dimension, you get invariance for isomorphism classes there. So that is again something that's follow-up of this paper which I mentioned, the 2005 paper of Dutt, Kodiala, and Sundar. Well, I think this approach is taken. So that's the reason why people study rigidity, for example, on algebraic structures. So there are various notions of rigidity, like geometric rigidity and algebraic rigidity. I think there's a whole school of people who school of thought which tries to look at various algebraic structures and try to identify what are the rigid objects there. So the rigidity translates to the orbits being closed. Does that answer your question?
Yes, but so I asked specifically about Hopf algebras. So I saw such things on associative algebras or Lie algebras,
Right.
but specifically about Hopf algebras.
So what? So I think I didn't follow. What about Hopf algebras is what you're trying to point to?
So you mentioned as a motivation for the study of these fixed tensor invariants, the problem of classifying Hopf algebra structures
Correct.
in a given dimension. And
Right.
I'm just asking if there is such a literature where in small dimensions people study this variety.
Right. There is some I think there's a paper due to Ehud Meir where he looks at all. I mean, he doesn't restrict to a certain dimension, but he looks at all Hopf algebras, the variety of Hopf algebras, and tries to understand it at that level. I think probably that's the kind of thing you're talking about. So he does some
Yes.
geometric invariant theory there on that variety. Yeah.
Thank you. So there seem to be no more questions, so let's thank the speaker again.
Thank you.
And we have a break.